Let's start. So I had Kōan 9. Unfortunately, I was the only active member in my group, so I had to do it alone. The task was to model an octopus and evolve some locomotion and to involve some new morphology. I did the first thing, and unfortunately, I had not the time to evolve the morphology. But I'll show you the first part of the task. So for starting, I played around with webbots, and there was an example called the Yamor robot. And this robot has these modules. In the rear, you have a connector. In front, you have a joint with a motor and also a connector. So yeah, with these modules, you can build a lot of different morphologies and just connect with these modules. And the first step for me was to play around with it and just to model a little worm like that. This is just 8 modules. And yeah.
Florian, we still see the front slide. Could you move to the...
Oh, maybe it doesn't work.
There we go. Yeah, okay. Now I can see it. Perfect. Perfect.
Yeah, I think it doesn't work in full screen. So can I do it this way? Do you see enough?
That's fine.
Okay. Yeah, this is the module I talked about with the front joint and motor and the rear connector. And I built up a little worm like that. And the question was, how to control it. And I put in every single module had a controller, just a simple controller, a sinusoidal controller with 4 parameters: the amplitude, frequency, offset, and phase. And no, not a feedback controller. So every single controller just depends on time, and there's no information changing through the different modules. So now the question was how to choose these parameters, and I used the evolution algorithm. So I had 7 modules because the last module doesn't control anything because the joint is just in the air. So I had these 7 modules, and every module had 4 parameters. So I had 28 dimensions in which I want to optimize the behavior. It was clear that the fitness function is just the distance the robots traveled after some time. I took 30 individuals and took the 10 best to survive. And 5 of the best 10 got no mutations. This is always good in evolution to take at least the first best without mutations, so you can assure that the evolution is not getting worse. And the rest of the individuals mutated with a gene selection probability of 8%. And I took a mutation width of 1.2. And in this range, about the old value, I choose the new value with a uniform distribution. So in a further step, you could use also a normal distribution, maybe would be better, but just for first step, I used the uniform distribution. And I didn't use recombination because in this experiment, all the modules and parameters were dependent on the upper parameters. And in this case, it's not so good to use recombination. It's just good if you have independent parameters. So I can show you a little video of my first experiment. hopefully, don't know, just works in full screen mode. No, it works. So do you see the video?
Yes, you can see it.
Cool. Okay, this is just a little selection of the evolution. I think it was generation 10 or something like this. And at the beginning, some not so good individuals, but yeah, it's also not so good. Yeah, but this was quite a good individual. And I think it's a really cool locomotion, like a real biological worm, or similar to it. Yeah, so this was my first step to come closer to the goal of the task. It was not so easy to do it in WebBots. So technically, because you have to use a so-called supervisor, which communicates with all the modules, and you have to synchronize all the stuff. Yeah, so was the first step, and then I went further to the Octopus and modeled a morphology, similar to an octopus. Actually, it's just a pentapus because I just used 5 tentacles and not 8. And you have a cylinder. This is the body with 5 connectors, and there you have with tentacles. And at the end effectors, I gave the end effectors a higher mass because in experiments it was a result that is better for movement, so it can control better this way. So yeah, now again, what is a good controller for it? I use again this oscillator controller, but not with an offset, because in this environment the offset is not so practically, because you have just a range for the joints. So and you can't go above the range. So the offset, or if the offset is too high, then you just got to the broad border of the joint range. So yeah, I didn't use it anymore, and have this parameters frequency, amplitude, and phase, and did again an evolution. Now I had 20 modules, because 5 tentacles with each of 4 modules. So I got this dimension of 60. I used 20 individuals, and the 10 of the best of them survived, and 3 of the best got no mutation, and the rest mutate with the same parameters as the evolution before. And didn't use recombination again, but I come to this recombination topic later. I show you just the first impression. So I have to say something about the physics, because in WebBots you actually have just physics for land and not for water. You can rewrite the physics engine, like in the example of the salamander, but yeah, not so easy. So my first try was just to lower the gravity to 0 and have octopus or the pentapus in space, and this was just the first locomotion. But there's no traveling, so because the center of mass is always at the same position in space. Sorry. So the pentapus became to a space panda-puts. And now I thought about the physics. I looked around in the web and I didn't find a good or easy way to model water. So maybe you have some suggestions later. But for first step, I lowered the gravity to 1 or 1.2 or something like this. I just had friction on the ground, but no friction in the water. I could use a damping parameter in water, which slows down a little bit the movement, but yeah, it's still no friction. And I couldn't use fluid dynamics because it's very complex or hard to compute, and there is no fluid dynamics in WebBots. So the problem is that if you have no friction in water and no fluid dynamics, it's actually impossible to move in this modeled water because it's like in space. But what you can do is that you push from the bottom and jump. Yeah, the panda-puts had the possibility to jump around in space. So I show you now some first individuals of the 10th generation. So you have a little locomotion, and the panda-put travels some centimeters. Yes, and now I show you some better individuals of a later generation. So sometimes you see, a similar locomotion to a fish or to a octopus. But as I said, it's actually not. It's not impossible to evolve a real octopus locomotion because you have not the water physics. So it's just pushing away from the ground, but was good enough for my possibilities because I had not so much time to model all the physics by my own. Because as I said, I was the only member of my group. Yeah, this was some evolved locomotions for the panda-puts. And now I give you a little outlook for future work. First of all, I would implement a physics engine for water because, as I said, just in this environment, it would be possible to evolve a real swimming locomotion. And next thing is I would use feedback controllers instead of just with sinusoidal controllers. For example, I would use fully connected neural networks because I think it would lead to a more natural locomotion because then the controller has information about the environment and information about the other controllers. For example, you could use as inputs the angle and the angle velocities of all joints and just combine it to in a neural network to the motor output. In my case, I use just with forward controllers, and it's actually like a pattern playing, so it has no sense of its environment. The next step could be to evolve some new morphologies. For example, use genetic programming, like the Carl Sims stuff. And I think for the Octopus, it would be useful to use recombination because you have this independent tentacles, and this would be maybe a cool thing to combine some good tentacles and not just to mutate on all the parameters. So if you have one individual with a good tentacle and another individual with another good tentacle, you could combine this the best tentacles of this individual. This would maybe lead to a quicker convergence or to a better performance of the evolution. Yeah, and maybe some other thoughts I could use I can use the symmetry of the Octopus and just gave every controller, every tentacle the same controller in the first generation. So in this way, I could compute much quicker. And then I would have some good individuals I could feed to another evolution where you just evolve all the modules independently. So maybe this would also lead to a better performance of the algorithm. Yeah. Thank you for your attention. Do you have any questions?
All right, thank you very much. Excellent presentation. Really well done, especially for only being one person. So I will pass the floor to the different TAs. Anyone want to start with questions? We have Avinash here now, so we'll start with Avinash.
Hi, Florian. Well, the first question is, if you mentioned that there were 7 modules in the, for example, looking back at the linear configuration, the worm morphology that you tried, you said there are 4 parameters per module since you have distributed controller, and then there were 28 total parameters that you have to optimize. So if you wanted to reduce the dimensionality of this one, and instead of 28 you wanted to have as few parameters as possible, so which parameters would you keep constant, and then which parameters would you have to optimize revolution to get locomotion gait? What according to you would the parameters be?
First of all, I would drop away the offset parameter, like in the Octopus, because I think for this example it's not so important. I think you could use a global amplitude for every controller, because it's not so important that the amplitude is different for the modules. Yeah, I think that the most important parameter is the phase parameter, because of this you can have in this sinus oscillation you can have a different position, so to say. Yeah, maybe you could also use the same frequency.
Right. Yeah. So maybe you did observe that the frequency would remain the same even after you evolved. Was that something that you observed, that the frequency always would remain more or less the same for all the modules? Was that something that was the result of the evolution?
Yeah.
Right. Yeah.
In the main part of the worm, yes, but just in the last module, maybe there was another frequency, but this module is not so important for the movement. Yeah.
Right. So and as a fitness function, so what was the fitness value that you used? Was it the absolute distance between the starting position? So it was the absolute distance, right?
Yeah. Okay. So the direction of travel was not important. It was just the Euclidean distance.
So just one other question. Did it so happen that every time in the linear configuration, when every time you did a fresh evolution, the direction of the locomotion, was it random, or was it always was the robot moving in one direction in each single evolution, or did it vary randomly?
it was not really random, but some individuals went in the upper direction, but the most individuals went in this direction as I showed in the video. But I think it's because I seeded it not really randomly, just in a distribution, and maybe because of that you had this first direction.
Okay.
So,
Okay. No, the what I meant was with each evolution that you ran, the resulting stable or the best evolved controller at the end of the evolution. So was the final result consistent, or did it vary? Like at end of first evolution, maybe it went one direction, and the second one it went the other. So was that the case, or did it always move in one single direction?
it was maybe 90% to one direction and 10% to the other one.
All right. Thank you.
Okay. Anyone else questions? If not, I have a couple. Okay. So thanks again. Really nice to see this presentation. I had first a bit of a technical question with WebBots. Was it difficult to integrate the algorithm to optimization algorithm with WebBots, or was that okay? Did you have any problems?
I had some little problems. I used Python, so I couldn't use because all the examples were in C. So I had to translate it a little bit, but actually I did all the stuff from scratch.
Oh,
so
nice.
It was easier for me, and maybe I learned more in this way. But I think it was a little bit complicated to communicate between the modules, because you can't just do it in the code. You have to do it by devices. You have to use this emitter and receiver devices.
Right.
And then you have to translate your information, for example, the gene in some string.
Right.
Then you can send the message and have you encode the whole string. So maybe it's a little bit complicated for programming, but actually it's quite cool, because then you go in the right direction. Like it's more like real robotics and real hardware.
Exactly. So it would be great to see if you could put your code. I don't know if you put it online yet, or open it up so other people can learn from it. That'd be fantastic.
Yeah, I can do it. Yeah.
Fantastic. So you didn't get to the part where you actually evolved both the controller and the morphology, right?
Yeah, unfortunately not.
So could you just comment, what do you think would be a benefit in this case of doing the two things at the same time? What do you think you would see?
It depends on the speed. Maybe you can if you just start with the body and no modules, then maybe something really cool and unexpected could evolve.
Right.
But yeah.
Right. Do you think it could be an idea to include some joints that are passive in the chain?
Yeah, it would be not so bad, I think.
Okay.
But there are a lot of things I could have done. So it's the question of time.
Yeah. No, but I think even the application you came up with, which was this space pentabot, I think that was kind of a cool idea, because I mean, if you're going to do planetary exploration, some of the problems you have is that you know approximately where you will land, no? And you know approximately what type of terrain, but you don't know exactly what type of obstacles or what type of rocks or sand you will encounter where you land. So maybe some type of space pentabot that could learn during a couple of hours to be able to move around would not be such a bad idea.
This is a very good point, Martin. I think it's a very good point.
I think we should notify NASA and ESA that we have a.
Yeah, we should inform NASA about this.
That they should employ Florian. So and then
at least ask for consultancy.
Exactly. And then finally, I just want to add that if you come tomorrow to the presentation of group 10, they've actually been playing around with the physics module of the salamander example to do a passively, well, partially passively compliant wing of a manta ray operating in water. So I'm not sure exactly what we'll see, but I think it will be pretty cool. So it might be something you can apply as well.
Yeah.
Any more questions?
Maybe I want to ask something about the, was it a technical difficulty or just your choice of not using the crossover?
Can you repeat the question?
Sorry. For example, in your evaluation, you chose 5 best, and for the remainings, you applied mutation, but according to the presentation, what I see that you didn't apply the crossover.
Yes.
So is this your just choice to simplify the algorithm, or were there a difficulty in the implementation to link with the webbots?
Yeah, no, there are no technical difficulties with it, but I didn't use it because I used it at the beginning, and it was just too much noise, I would say, in the algorithm. Because at the first step, I had the result that it's not so good to use recombination because every single module was dependent on the other modules, and it would be not so so good to just
it's interesting because like what I remember from my experience, like crossover can cause like more smooth leading to the like minimal. So normally mutation is the less random selection in the evolution. So it actually is quite interesting from that perspective.
Yeah, maybe I think it's always the question of how to do the recombination, and maybe I could have done to recombinate the whole module packages. So just to take one module of the one individual and one module of the other, so the 4 parameters together, maybe this would be good, because then you have kind of an independency. But actually it makes no sense to recombine some random parameters of some different modules, I think.
For one other question, not about the algorithm, but like about the behavior, like which do you think will be like easier or better performance in the motion, like this worm-like behavior or snake-like behavior? You know, snakes move like in a horizontal direction when they move. So which do you think will be easier to find the like optimal motion?
I didn't try the snake-like locomotion because it's a question of the start position, and my worm laid down on his bottom, so it just would move this vertical direction, but maybe physically it's better to have the snake-like motion.
Actually, I'm not sure about that either. Just
I don't know. Just I can try it in some later experiment.
Actually, it would be nice to evolve the joint to increase the like maybe degree of freedom to evolve from worm behavior to snake behavior according to terrain.
Yeah. Would be cool.
Thanks a lot.
All right. Any more questions, comments?
No, just thanks for the great work.
Exactly. I second that. All right. Thank you.
Yeah, thank you.